Hi and welcome back to SWK 122 Workbox. Let's talk about what we'll be doing in this section. So we're going to cover scalars and vectors, vector operations, parallelogram and triangle rule. So without any waste of time, let's jump into it. So we are on unit 1.2 according to the study guide. And this unit is titled Geometric Vector Operations. This is found on chapter 2 in the textbook from 2.1 to 2.3. All physical quantities in engineering are either given in terms of scalar or vector form. So we have quantities, which can be given in scalar form or vector form. So today we're going to be talking about scalars and vectors. So let's start by defining what's a scalar. A scalar is any positive or negative physical quantity that can be described using magnitude. So this scalar, anything that you can describe using only magnitude, will fall under the concept of scalar. For example, we'll talk about length, time, and mass. So this is how we define scalar. So now let's define what's a vector. So a vector will be defined as anything, not anything though, let's just say any physical quantity that requires both magnitude and direction to be fully defined. And for example, here we're talking about forces, positions, and moments. Right. Without any waste of time, let's talk about how a vector is represented. So we're talking about representation of vectors. So the first thing that we'll talk about is how we write or we show this is a vector when we're writing. So you can either use a bold capital letter A to give a vector a name, as in like vector A, or you can use an A with a bar at the top. This is the most commonly used one, and it's easier for one to write, unlike trying to make a bold A. Secondly, is to note that the size, let's just say the length of the arrow represent the magnitude of the vector. Right, so let's say we have a vector given in this form. Let's call that vector A. So use an A with the bar at the top. This vector is at an angle, say we have an x-axis, so it's at an angle theta from the x-axis. So as we have discussed, we said the length of the arrow represents the magnitude, while the angle theta represents the direction of the vector. So this is how we represent a vector in writing. So let's move on to what we call vector operations. Vector operations can be divided into 4 sections. So with the first one being multiplication of a scalar of a vector by a scalar, division of a vector by a scalar, then we have addition of vectors and subtraction of vectors. So let's start by talking about the multiplication of a vector by a scalar. So say we have a vector, let me write it a bit up. So say we have a vector A, and we take that vector, we multiply it by a scalar of a magnitude of 2, positive. So what will happen to the vector is that the vector will be enlarged by a factor of 2. So this time we'll have 2 times the vector A. So now let's move on and take a vector, the very same vector A. Now let's multiply it by a negative vector. So what happens is that when you multiply a vector by a scalar negative 2 of negative 2, the direction of the vector will change. So it will have the same magnitude as the above example, but the sense and the direction, or the direction will change. So that's all we have on multiplication of vectors. So now let's move on division of vectors by a scalar. There. So now we're going to use the very same example of having a vector A. So we're taking that vector, we're dividing it by scalar of 2. So what will happen now is that the very same vector that we had A will now be reduced by a factor of 2. So that will mean we'll have a 0.5 vector A. Same will happen if we take the negative scalar. So the sense of the vector will change. So now let's move on to addition of vectors. So here on addition of vectors, we'll learn about two methods that we can use to add vectors. So the first one that we'll know is that we can use the parallelogram rule, and secondly we can use the triangle rule. Right. So all vector quantities obey the parallelogram rule of addition. So let's say, okay, I'll do this by giving an example and show how vector addition is done on a parallelogram rule and in a triangle rule. So let's say we have two vectors. Say we have two vectors. So we have vector A and another vector B. Right. So if we were to add these two vectors using a parallelogram rule, then we'll have this thing. So the parallelogram rule say we must add the two vectors tail to tail first. So draw the two vectors tail to tail. So we'll have vector A and vector B. After that is done, we're going to have to draw a line parallel to vector A and a line parallel to vector B. And where that the two lines intersect, let's call it point P. So point P will be a stop region for the vector or the resultant force, or let's say for the resultant vector in this case. So we'll have a vector, let's call it R. Right. So the resultant vector, remember we were adding vector A to vector B. So that's all you have to do when you're doing vector addition using a parallelogram rule. So now let's say we're doing vector addition. I'll just try to divide this into two here. So now we're using, okay, this was the parallelogram. Rule. So now we're going to talk about the triangle rule. Right. So say we have the same parallelogram rule, because the vector rule, the triangle rule arises directly from the parallelogram rule. So say we have the same vector A and B. So the parallelogram rule says we have, you first draw the vector A, right? So if you have adding vector A, vector B to vector A, you start by saying vector A. So that's the first thing that you do. You draw your vector A, then you draw your vector B, but in a certain order. So if I'm adding A to B, what I'll do is that I'll draw my vector B's tail at the tip of vector A. So this will be now my vector B. Remember, we're still using this example right here, right? We're using this example right there. So I still have my vector A. So with the tip ends, I'll draw my tail of my vector B, right? So my vector, then now my resultant vector, let's call it R. So my resultant vector will be A, vector A plus vector B. So that's how you do your vector addition using the two methods. Remember, the triangle rule comes directly from the parallelogram rule. So now let's talk about subtractions of vectors. So we're still going to use the same concept as we've used in vector additions, parallelogram and triangle rule. So say we have vector A that needs to be added to vector B, right? So the first thing that you do is you draw your vector A All right, and remember, okay, let me draw it a bit further. So you have vector A, and this time you're subtracting. So if you're subtracting, you're going in the opposite direction as vector A. So I'm subtracting vector B. Remember I said you draw the tail, you draw them tail to tail. So this will be your vector B. Right? So remember, you're still using a parallelogram rule. So you draw a line parallel to vector A and another line parallel to vector B. Right? And starting from where the tails of the two things going to the point where the two parallel lines intersected, you're going to have your resultant vector. Let's call it R. So therefore, your resultant vector is going to be A subtracting B. That's how you do vector subtraction. So the same is going to be with vector subtraction using triangular rule. So remember we said I'm going to use a different color. So the first thing that you do with the triangular rule, we're taking A subtracting vector B. So what you have is that now you have vector A being in that direction. Remember triangular rule, you use tip to tail. So you're subtracting vector B, so the tail will start at the tip of vector A. So you have vector B, right? And the resultant force R will be vector A subtracting vector B. So that's how you do your vector subtraction. So in mechanics, we have two problems. It's either we're going to calculate the resultant force, knowing the components, or we're going to resolve the components from the resultant force. So let's talk about forces in mechanics. So this, let's just call it vector addition of forces. So we said we have two problems. So we have one where we have to find the resultant force, and one where we have to determine the force components. So let's do a quick recap on them. So, but this time let's assume we're using forces. So let's say we have like a pin and one guy pulling with a rope with a force of F1 and another guy pulling in that direction with a force of F2. Remember vectors. So say the question says to you, determine the resultant force. So what you do again, remember, if we're using parallelogram rule, let's write them here. So parallelogram rule, and still have space down there, and triangle rule. So if I'm adding vector A to B, remember we're using tail to tail to start off our vector addition. But in the triangle rule, I'm using tip to tail. So you take the tip of the previous vector to the tail of the next vector that you're adding. So these are the most important things that you must keep in mind, right? So let's focus on our example. So let's say we draw our F1 like that. We're doing the parallelogram rule. So that's our F1. So if we're doing parallelogram rule, you say tail to tail. So I'm going to add my second vector, which is f2, right there, right? So remember, after that you draw a line parallel to f1 and a line parallel to f2, vector as vectors. So the resultant force will start from the tails to the point where they intersect. So that's how you do your parallelogram rule. So your resultant force, let's call it FR. FR will be F1 plus F2. That's your parallelogram rule. So now let's do our triangle rule. So we're adding F1 to F2, right? We're finding the resultant force. So what you'll have is that if you have your F1 right there, so now I need to draw the tail of F2 starting from the tip of F1 because it's tip to tail, right? So that will be my F2. Then my resultant force FR will be that. Or one can decide to add F2 to F1, which will still be the same thing. So, but if we have to do vector representation of it, so we'll first draw our F2. So our F2 will go that way. Then our FR, this will be F2. So your F1 will start from the tip of F2. So you have your F2, F1 going like that. Therefore your resultant force will still be the same as the previous one. Another thing, let's talk about resolving when you want to resolve the components of the forces. All right. So this method will come in hand when one wants to study what's the effect of a pulling or what's the effect of the pushing force. So that means you can now focus on the pulling force and focus on the pushing force. So all you have to do, say you have a vector, say that's a guy, that's a pin there and a guy pulling it with a rope with F. Alright, let's call it F1. That's a vector. So you want to know what's the effect of this guy, what's the effect of the amount of force in the X direction, and what's the effect of the amount of force in the Y direction. So then you can resolve your forces. So then resolving it means you'll have your Fy and your Fx. That's all we mean when we're talking about finding the components. So now you have all the components. You have the X component of F1 and the Y component of F1. So we're going to do examples on the next session. Thank you. Let's meet on the next one.